Hi folks, this video will act as a review for your second exam, which is coming up next week. It contains 3 practice problems, which you can do on your own, and then immediately check your own answer, and I'll walk you through how we got to those answers, which I think is the best way to study for this exam. Before we do that, though, I want to give you a heads up about what exactly will be on the exam. It'll be the same format as it's been in the past, so I'll send you a data file, send you a list of questions to answer. You'll write up the answers to those questions in APA format and email your answers back to me in a Word document. There is a little bit of stuff that was on the previous exam that will also be on this exam. That's why I wanted to give you a heads up about it. You should know how to run a simple linear regression, which I'm sure you know by now. You should also know how to interpret the values of alpha and beta, which is also something you had to do on the last exam. Unstandardized beta, just to be clear. And then the majority of the exam will focus on what we've covered since the last exam, namely hierarchical regression and how to test for interactions using regression, specifically using process. So you won't have to do any of the longhand stuff that we did in class for the exam. You'll be able to use process for any question that asks you to test for an interaction. So you should certainly know how to run a hierarchical regression, adding predictors a few at a time to see which ones improve the model and which don't. You should also be familiar with how to check for collinearity between predictors, which is something we talked about a few weeks ago. And then with respect to interactions, make sure you know how to use process to test for interactions both between 2 continuous variables as well as interactions between 1 continuous and 1 categorical variable. You'll also need to know how to use process to generate graphs that show your findings. And of course, you can also use process to take care of the mean centering and dummy coding that you would need to do for analyses like that. With that as background, let's now go into our first practice problem. Previous research has identified both education level and the availability of alcohol as predictors of the frequency of domestic violence incidents. Earlier this year, Blake et al. Published a study to see whether the frequency of misogynistic tweets that were sent in a given area would further predict the frequency of domestic violence incidents above and beyond education level and alcohol availability. So this was actually kind of a clever study. They obtained literally millions of tweets, publicly available Twitter data, and for various regions around the United States, they calculated, as we'll see on the next slide, the percentage of people who have a college degree in that area, the number of liquor stores that exist in that area, and the number of geotagged misogynistic tweets that were sent by people from that area. As you can probably tell, we're setting up for a hierarchical regression here to see whether the model with 3 predictors, including misogynistic tweets, predicts the number of domestic violence incidents better than just the other 2 predictors without the tweets variable. So for this practice problem, you would use the data file called misogyny.sav. There were 466 regions of the United States that the researchers coded. And for each of those regions, we know 3 things. We know the number of domestic violence incidents that were reported in the year 2013. We know the percentage of residents in that region who held a college degree in 2013. We know the number of liquor stores that were approved for off-site liquor consumption in 2013. And we also know the number of misogynistic tweets that were sent from that region in 2013. So using those 4 variables, what you'll do is first check for collinearity among the 3 predictors. We talked about 2 ways of doing this in class, and you can do either way in this case. Then you will build a hierarchical regression where you have college education and liquor stores in step 1, and then you will add tweets to the model as a 3rd predictor in step 2. I want to know if adding misogynistic tweets to the model made it better. In other words, was block 2 better than block 1? Also, as part of your answer, include a table that for each of the predictors in both steps, step 1 and step 2, that shows unstandardized beta and the p-value, either the exact p-value or you can use asterisks to indicate the p-value for each of those predictors. So if you'd like to do this practice problem, now is the time to pause the video, and then I will go through the answer with you. Okay, let's tackle this practice problem. So first you would have checked for collinearity. The two ways we could do that are either by producing a simple table of Pearson correlations, which we have on the left, or we can check the box when running a regression to request more formal collinearity statistics called tolerance and VIF, which would come up as part of your regression output for each of the predictors. If we look first at the correlations table, we see that there was a strong positive correlation between the number of liquor stores and the number of misogynistic tweets from a given region. You'll recall from class that we're generally concerned when we see strong correlations above 0.8 or below negative 0.8 between two of our predictors. So if we were to look at the Pearson correlation table, we would have concerns that the assumption of independent predictors is violated, that we have collinearity here. However, if we look at our collinearity statistics in our regression output, we see, not surprisingly, that those same variables that are strongly correlated with each other also have relatively high VIF values and relatively low tolerance values. But you'll remember in class we talked about using a cutoff of 5 for the VIF, and neither of these is above 5. So here we have a situation where our two ways of testing for collinearity actually give us different results. The correlation tables tell us we have concerns, the VIF values tell us we don't have concerns. So you could use either of these here, but your conclusion will depend on which one you use. So for the purposes of this video, we're going to assume that collinearity is met. We're going to proceed with the analysis, and we're going to run the hierarchical regression that I described earlier. In our model summary table, we have two models. Model 1 only has two predictors, liquor stores and college education. Model 2 has three predictors, liquor stores, college education, and misogynistic tweets. Model 1 was significant, so knowing liquor stores and education level was significantly better than knowing nothing. That's not surprising, given that previous research found the same thing. And if we look down at our coefficients table, we see that both of those variables, both education level and alcohol availability, were significant predictors of the frequency of domestic violence incidents. And if you look at the two standardized beta values, 0.45 and 0.15, you see that liquor stores was actually a much stronger predictor than education level was. That's not exactly what we were looking for, though. What we were looking for was to see if adding tweets to the model made the model better. And indeed, if we look at the F-change test for Model 2, the significant F-change test tells us that adding misogynistic tweets as a third predictor made our model significantly better. Whereas our first model only explained about 24% of the variance in domestic violence incidents, our second model explained about 28%. In other words, adding tweets as a third predictor increased our R-squared value by about 4%. If we look at our coefficients table, we see that college education is still a significant predictor of domestic violence incidents. Liquor stores, however, is no longer a significant predictor, statistically speaking. And finally, misogynistic tweets was indeed a significant positive predictor of domestic violence. Regions that had more misogynistic tweets also tended to have more reported incidents of domestic violence. So how will we write up our results? First, it's nice to start with a sentence that summarizes what we did. So we ran a hierarchical regression to see if misogynistic tweets predicted domestic violence even after controlling for education level and alcohol availability by including them in block 1. Model 1 was indeed significant. Those two predictors explained 24.2% of the variance, and both of them individually were significant predictors, as shown in Table 1. Here are those two unstandardized beta coefficients from Model 1 for education level and alcohol availability, both of which were highly statistically significant. However, and more importantly, Model 2 was significantly better than Model 1. Here are the results of our F-change test from the previous slide, and we noted that Model 2 explained an additional 3.7% of the variance. If we look back at Table 1, we see that the significance went away for alcohol availability, but the other two predictors, education level and misogynistic tweets, were both statistically significant, and of the two, misogynistic tweets was the stronger predictor. That is the end of practice problem number 1. Practice problem number 2. This, again, I think was a very clever study, although I don't envy the person who had to write the IRB application for this study. This was actually a field experiment where they wanted to see if they could lure children away from a playground. So they had a confederate, a stranger, walk up to a preschool playground and ask the child essentially to come with them. And they wanted to see if the age of the child would predict their hesitation. How long did it take them to decide that they would indeed go with this person? Now, there was another variable in this study, which is what exactly the stranger said to the child. When trying to lure the child away from the playground, the stranger either provided accurate information or inaccurate information. So here's what the stranger actually said. I know your mother. Her name is blank. She said you have a teacher named blank. I have a gift that I want to give you. Let's go together and get it. And then they would try to get the child to come with them. Now, in some cases, they would give accurate information, meaning they actually knew the mother's name or they actually knew the teacher's name. In other cases, they would give the wrong names for the mom and the teacher. So here we have two predictors. We have the age of the child, which is of course continuous, and we also have a categorical predictor, which is whether the stranger gave accurate information or inaccurate information. We want to see how those two predictors might predict the hesitancy of the child to go with the stranger as measured by how many seconds they waited before leaving. Our data file for this practice problem is called strangers.sav. Alarmingly, in this study, a full 50% of the children actually did leave with the Confederate stranger. This data file only contains data for the 60 children who did leave with the stranger. For each child who did leave with them, we know how old they were. They were either 3, 4, 5, or 6 years old, which we're going to treat as a continuous variable. We know whether they were given accurate or inaccurate information, and we know how long they hesitated, which was measured in seconds, before leaving with the stranger. So using these three variables, you would now answer the following questions. First, did a child's age predict how long they hesitated before leaving with the stranger? And second, and more importantly, did that relationship depend on whether the child was given accurate or inaccurate information? So you can answer both of these questions by running a single regression where you include age, information, and the interaction between age and information, all three of those things, as predictors of hesitancy measured in seconds. If you want to complete this practice problem on your own, please pause the video now. Okay, let's look at the results. This is one that we would run in process. So we would include age as our predictor, hesitation as our outcome, and information as our W variable, our moderator, in process model 1. Here is what the output from process is going to look like. We're going to cut right to the chase here. Age and information both were significant predictors of hesitation time. So age was actually a negative predictor, meaning as age went up, hesitation time went down. So in other words, overall, older children were less hesitant about leaving with a stranger. Information was also a negative predictor. Now, if you know that information was coded as 0 equals inaccurate, and 1 equals accurate, what that would tell you is that children who were given accurate information were less hesitant. They were faster to leave with the stranger. Importantly, though, both of those significant effects were qualified by a significant interaction between age and information accuracy, as shown in the highlighted purple area, which is the equivalent of the F-change test that we saw previously. So to make sense of this interaction, what we have to do is run separate simple regressions for our two conditions. In other words, a regression using only kids who were given inaccurate information and a regression for only kids who were given accurate information. As shown in the green area, kids who were given inaccurate information did show a significant negative relationship between age and hesitation time. But for kids who were given accurate information, there was no relationship between age and hesitation time. So in other words, age was a significant predictor of how long a child hesitated, but only if that child was given inaccurate information. Here's how we would write up our results. We can cut right to the chase here and just say that we found a significant interaction. We should still list our predictors and our outcome in that sentence. Then, to make sense of that interaction, we ran follow-up simple regressions, one with the inaccurate group, one with the accurate group. And what we found was that age was a negative predictor of hesitation time when the stranger gave inaccurate information. So in other words, only for kids that were given inaccurate information was it the case that older kids were less hesitant in leaving with them. However, for kids who were given accurate information, there was no relationship between age and hesitation time. Here's the graph from process, which we can get using the syntax that we request in the process output. It doesn't give us lines, but I've superimposed lines here. The blue line is for kids who were given inaccurate information. The red line is for kids who were given accurate information. You can see the dramatic difference in the slopes of those two lines, which is responsible for our interaction. That's the end of our second practice problem. For our third practice problem, prior research has indicated that physical activity is negatively correlated with depression and positively correlated with self-esteem. Generally speaking, people who are more physically active tend to be less depressed and to have higher self-esteem. In this study, the authors wanted to see if this same relationship holds true for youth who identify as either sexual or gender minorities. Furthermore, they also asked the LGBTQ children who participated in this study about the extent to which they're bullied for their LGBTQ identity. The researchers hypothesized that the relationship between physical activity and self-esteem might depend on the extent to which the children experience bullying. The data file for this practice problem is called bullying.sav. For each child who participated, and remember all of the participants identified as LGBTQ, we know three things about them. We know their self-reported level of physical activity, measured on a scale from 0 to 54. We know their self-reported level of self-esteem, which was coincidentally also measured on a scale from 0 to 54. And we know the frequency with which they experience bullying for their sexual or gender identity, which was measured on a scale from 0 to 4. So unlike in the last problem, where we had one continuous predictor and one categorical predictor, in this problem we have two continuous predictors, physical activity and bullying frequency, plus their interaction, both as predictors of self-esteem level. So try to answer the following questions. First, did either of these variables predict self-esteem on its own? Was there a main effect of physical activity and or a main effect of bullying frequency? Also, was there a significant interaction between those two things? In other words, did the relationship between physical activity and self-esteem depend on the frequency with which a child was bullied? And if so, what did that interaction look like? If you'd like to complete this practice problem, Please pause the video now, and then we'll go over the answer together. Okay, so we would again use process for this problem. Our moderator variable would be bullying frequency, our predictor would be physical activity, and our outcome would be self-esteem. We would check all the usual options that we do with respect to mean centering and requesting syntax for the graphs and making sure that our simple slopes analysis is centered at plus or minus 1 standard deviation if it's necessary. Here is the output from process. There was neither a main effect of physical activity nor a main effect of bullying. Neither of those variables on their own predicted self-esteem. However, we did find a significant interaction such that the relationship between physical activity and self-esteem somehow depended on bullying. Our p-value here is just barely below 0.05. So to make sense of this, we have to perform a simple slopes analysis. And here highlighted in royal blue, we have 3 levels of bullying. We have children who experience relatively little bullying, children who experience an average amount of bullying, and then children who experience a relatively high amount of bullying. What we see here from the 3 p-values is that this relationship is only significant for children who are bullied relatively infrequently. In other words, there is a benefit of physical activity on a child's self-esteem, but it appears that that benefit goes away if the child experiences an average or high amount of bullying. How would we write up our results? First, we will add a sentence that explains our model. We used physical activity, bullying frequency, and the interaction between those 2 things as predictors of self-esteem in a sample of LGBTQ youth. Neither of our predictors had significant effects on their own. However, we did find a significant interaction, so as always, we will graph that interaction. Our simple slopes analysis told us that physical activity was a significant predictor of self-esteem only for children who were bullied infrequently. In other words, for those who were low in bullying. However, for those who were average or high in bullying, that relationship went away. The benefits of physical activity for self-esteem were not seen for those children. Again, here we have our simple slopes graph. Our blue line shows us the relationship for children who experience little bullying. Red line is average bullying. Green line is high amounts of bullying. So you can see how the slope of the line changes as children experience more bullying. The relationship between physical activity and self-esteem goes away the more bullying these children experience. That's it for practice problem 3. Of course, if you have any questions, you can always shoot me an email, either before the exam or while you're completing it. And I wish you good luck, and I'll see you in 2 weeks.